So today's lecture is about increasing and decreasing functions. As you see, this is one of the functions that we have. And the question is, on what intervals is the function increasing or decreasing? Let's check. Let's look at the first part from a to b. You can see that the function is increasing on the interval from a to b. Why? Because the y values are increasing as x is increasing. What about from b to c? As you can see, it's decreasing. What about from c to d? It is increasing. So in one function, we can have both increasing and decreasing intervals. So if I would like to describe this function, I would say that this function is increasing from a to b, decreasing from b to c, and then increasing again from c to d. For the same function, what can we say about the first derivative? Remember, f dash of x or f prime of x is the slope. So what can you say about the slope in here and the slope in there? If you notice that increasing functions from a to b, it's increasing, you will find that the slope is positive. The slope has a positive value. While from b to c, which is a decreasing function, the slope is decreasing, or the slope has a negative value. From c to d, it's increasing, the slope has positive value. So from this, we can sum up that increasing functions have a positive slope, decreasing functions have negative slopes. And from here came the increasing-decreasing test. If the first derivative is positive or greater than 0 on a certain interval, then the function is increasing on that interval. If the first derivative is negative or less than 0 on an interval, then the function is decreasing on this interval. From here came the first derivative test. Okay, so what are the steps that we can do to find increasing or decreasing function and then find local extrema? If you remember, local extrema means local max, local minimum. So the steps are, first step, I need to find the critical number or numbers, because they might be more than one, by setting the derivative to 0 or does not exist. Do you remember the rule of finding critical numbers? So first derivative equals 0 or does not exist. First step. Second step, I will draw the number line and define on it the 2 or 3 or maybe 1 critical number that I found, and I will define the interval before and after each of the defined critical points. Then I will start substitute with the numbers within each interval and find if the first derivative is greater than 0, then my function is increasing. If it is less than 0, my function is decreasing. If the function is increasing then decreasing, just like this one, function is increasing then decreasing, then the point of change in the behavior of the function is called local max, as you can see here. If my function would be decreasing then increasing, so the point where there is the change in the behavior will be the local minimum. All right, let's start with examples. Always examples make it easier. Check intervals where this function is increasing or decreasing and then find if there is any local extreme. Okay, let's summarize what I need to do. I need to find the first derivative and set it to 0. Then I will find the critical numbers. I will define the different intervals and check the sign of the first derivative. So here comes the function, and then I will find the critical number by setting the derivative to 0. The derivative is 3x squared plus 6x minus 9, and then I will equal it to 0, and then I will solve for x. I will find that x equals 1, and from this bracket x equals negative 3. So I do or draw my number line. I define the two critical points, x equal negative 3 and x equal 1. If you have two critical points, then you will have 3 intervals. So the first interval will be when x less than negative 3, this part. I have another interval from negative 3 to 1. I have another interval from 1 to infinity. Alright, so the first step, I set the derivative to 0. I found the two critical numbers and I put them on my number line, and I'm starting to check intervals before and after each critical. Then I do my famous table. The first column is the interval, the three intervals I found, less than -3, from -3 to 1, greater than 1. Then the second column is called x value, which means I'm going to choose any x value in this interval. Usually go for the easiest ones. And then you're going to substitute this x value in the first derivative function and check the value. Is it greater than 0 or less than 0? So let's see the first row. The interval was x less than -3. I chose x equal -4. I substituted in the derivative function, in the f dash x function, f dash of -4. I found it 15 greater than 0 positive, so the function is increasing. The second interval was from -3 to 1. I chose the easiest point, x equals 0. You can choose any point between -3 to 1, any value in the interval. Then you substitute in the first derivative equation, and you found -9, negative, so it's decreasing. The last interval, x greater than 1, I chose x equal 2, and then I substituted in the equation. I found a positive value, so it is increasing. Therefore, increasing then decreasing function. Here at x equal -3, I'm having a change in the behavior of the function, increasing then decreasing, so I have a local maximum. So f of -3 is a local maximum. And then at f equal 1, I have a decreasing, then increasing function, decreasing, then increasing, so you will have a local minimum. So here f of 1 is a local minimum. Alright, so the steps are, when you do the first derivative, you find the x values, the critical numbers, when the first derivative equals 0. You define the intervals. You choose points in each interval. You substitute and you check the value. Is it positive or negative? Alright, just as we did in increasing versus decreasing function, another property is concavity. Is it concave up or concave down? So here are two graphs that we have. I have this function from a to b. And by the way, the two graphs are increasing, and this function a to b is increasing. If I wanted to draw a tangent line in the middle of the function, you will find that the tangent line here is below the function, while the tangent line here is above the function. So what does this mean? Both functions are increasing, and thus both of them, their slope is positive. The slope is increasing in both of the functions. But there is a difference, is that here the slope is increasing with an increasing rate. So f dash is increasing with x, while g dash is decreasing with x. Here g dash, the value of the derivative itself, is decreasing. Here it's very steep. Here, as you can see, it's getting more horizontal, while here it's the opposite. So here it's increasing, the slope value is increasing as x is increasing. Here the slope value is decreasing while x is decreasing. So this one we call concave up, and I always say it's a happy face, as if it's a mouth, a happy mouth. And this one concave down, or a sad face. So in this function, can we define what's concave up or concave down? Yes, this part from a to b, as you see, like sad, the mouse is downward, so concave down. From b to c, concave up. From c to d, concave down. From d to e, concave up. From e to p, still concave up. From p to q, concave down. Alright, how to do it using the derivative? Well, if the second derivative is positive, then the graph is concave up. If the second derivative of x is negative, then the graph will be concave down. So here are the steps. I will set the second derivative to 0 or does not exist, and I will solve for x. I will define the intervals before and after each of the critical point of the second derivative test. I will substitute with a number, and then I will check if it is positive or negative. If it is positive, concave up. If the second derivative negative, concave down. Let's go to an example and make sure we do understand what's going on. So here is the function, and he wants to know where this function is just concave down. So this is my function. I did the first derivative, and then I did the second derivative of the function. So the first derivative was 12x cubed minus 48x squared plus 48x. Second derivative will be 36x squared minus 96x plus 48, and I will set it to 0. Since all of them are divisible by 12, so I divided by 12, and I set the function to 0. 3x squared minus 8x plus 4 equals 0. This is the second derivative. So I'm solving for x. I found x equal 2 over 3 and x equal 2. I put my 2 over 3 point. I put x equal 2, 2 critical points. So I have 3 intervals. So here x less than 2 over 3. Here x between 2 over 3 and 2. And here x greater than 2. I do my table with the 3 intervals. I choose points in each interval, any point you want to choose in the interval, and here instead of f dash x for increasing decreasing, it's now f double dash x to know if it's concave up or down. Substitute it in the first one: positive concave up, negative concave down, positive concave up. The question was asking about the interval where it is concave down, so this is from 2 over 3 to 2. Another important thing to identify in the function is if there's inflection points. Inflection points are the points where simply the graph changes its concavity, either from concave up to concave down or from concave down to concave up. Any change in concavity is called inflection point. And inflection points are just found like local extrema. Do you remember local extrema when we were finding if the function is increasing then decreasing or vice versa? I have an extrema. So also here, if the function is changing concavity from concave up to concave down or vice versa, then there is an inflection point. And there is also where I'm having a second derivative change in the. So let's check this one, this example. Find all inflection points in this function. So inflection point means I need to check concavity, and if there is change in the concavity, it will be inflection. To find concavity, I need to set the second derivative to 0 and solve for it and check the sign of it. So here is the first derivative of the function. So it's gonna be 2x cubed plus 3x squared minus 12x. Second derivative will be 6x squared plus 6x minus 12. I will set it to 0. I will solve for x. I found x equal negative 2, x equal 1. Here are my 2 points on the number line, and I need to check the 3 intervals and see. Here are the 3 intervals. I chose any x value in each interval, and I substituted in the second derivative equation. And here the first one positive, so concave up, negative concave down, positive concave up. So I have actually from concave up to concave down, here I have an inflection point at f equal negative 2. And then from concave down to concave up, I will have another inflection at x equals 1. There is actually another way to find extrema, which is if you know that your function is actually concave up, then you know that you have a local minimum. If you know that your function is concave up, then you know that you have a local max. So if you do the first derivative to 0 and then substitute in the second derivative, remember if the second derivative is positive, then it is concave up. If concave up, then you have a local minimum. If you do the first derivative and then you substitute in the second derivative, if it is negative, then you have a local max. This is another way to find the extrema, although I prefer more to do the increasing, decreasing because it's easier. This is our last example, which is about the graph. For this graph, I want to find everything. The function is 4 plus 3x minus x cubed, and I need to know the intervals of increase and decrease, local max, local minimum, intervals of concavity, inflection point, and sketch the graph. Okay, let's recap. Increase decreasing function, I will set the first derivative to 0, find the intervals, and find if the function is positive or negative by substituting in the first derivative. Local max, local minimum, I have them if there is change in the increase decrease. If it is increasing, then decreasing will be local max. If it is decreasing, then increasing, it will be local minimum. Concavity, I need to check the second derivative, and if the second derivative is positive, it is concave up. If negative, concave down. Inflection point, if there is change in the concavity. Example by steps. So here is just what I said. I will use the sign of the first derivative to decide if it is increasing or decreasing. Local max minimum, I will do it using the first derivative test, and then I will decide if my function is concave up or down using the second derivative, and from it I will find the action point. So here it is. This is the function, and this is the first derivative. I will set the first derivative to 0, and I solve x is positive or negative 1. Since I have two values, then I will have three intervals, from negative infinity to negative 1, from negative 1 to 1, and from 1 to infinity. I will choose point in each interval. Here I choose x equals negative 2, here I choose x equals 0, and here I choose x equals 2. I will substitute in the first derivative equation, which is this one. So this will be 3 minus 3 times negative 2 squared, and the value is less than 0, so it's a decreasing function. It's decreasing on this interval. Then at x equals 0, f dash x will be equal to 3, which is greater than 0, increasing. And then at x equal 2, it will be less than 0, so it is decreasing. Then, if decreasing then increasing, then I will have a local minimum. So f of negative 1 equals 2. I will have a local minimum at the point of intersection between the two intervals, which is negative 1. And then, if I have increasing then decreasing, then I will have a local max at 1, which is the intersection of the two intervals. So f of 1 equals 6 is local max. The 2 and the 6, we got them from substituting in the original equation. Alright? Not any differentiated equation, in the original equation. Now I'm getting to the second derivative. I solve the second derivative to be negative 6x. To set it equal to 0, so x equals 0. I have one critical point, so I just have two intervals, x less than 0 and x greater than 0. I chose easiest point, negative 1 and 1, and I substituted in the second derivative equation, which is minus 6x. So this will actually be equal to 6 greater than 0, so concave up. This will be negative 6, so less than 0, concave down. If I have concave up, then concave down, then I will have at x equals 0 inflection point, because I have a change in concavity. So f of 0 equals 4 is an inflection point. Here is sketching the graph. As you see, up till 0 is concave up, and then from 0 to infinity is concave down. At 0, 4 inflection point. Negative 1, 2, I have my local minimum, and at 1, 6, I have my local max. So I just applied everything I got to make me capable of drawing my sketch.